Hello everyone. Today I want to give you some lectures on the discrete Fourier transformations and the reciprocal lattice. The reciprocal lattice is a very important part in the solid-state physics. In many traditional textbooks, they only give you the definitions of the reciprocal lattice from the real space, but they never tell you why and what is the Brownian zone. In today's lectures, I want to introduce how to derive the reciprocal lattice from the discrete Fourier transformations. First of all, let's review the Brownian zone in the one-dimensional lattice. It has the interval A, and its reciprocal lattice will becomes to 2n a 2 pi. In real lattice is A, and the reciprocal lattice it becomes to 2 pi, and the Brownian zone is minus pi over 2a and pi over 2a. So today's main topics is I want to tell you why we want to give such kind of the definitions, and in 3 dimensionals, and why the reciprocal lattice it can be written in such kind of the form. Cross product A1. This means the cross product. And the B3 is 2 pi times A1 cross product A2 minus V. Now V can be written in the volume. This is the mixed product. A3 2. So before we start, let's introduce the discrete Fourier transformation. Let's make a correction. This should be written pi minus a to pi over a. So in the discrete Fourier transformation, the basic definition is that we have the endpoint. They can be any kinds of or review as a data or the function, such as the wave function. It has the periodic boundary condition. Which means the n plus n equals to xn. These endpoints can be written in a set x0, x1, x2 to xn minus 1. This matches the definitions in the computer science and in the mathematics. This is a very common definitions of the endpoints. So let's define its discrete transformations. Often we can define their discrete transformation in such kinds of way. In this way, xkf equals to this is the normalized constant and it can be defined in this one or this. They are all okay, but in physics we often define in square n, in n root. Some n 0, some n from n minus 1, xn e minus I 2 pi and k over n. There are some properties of the such kinds of the this term. So the first property is the sigma k, some k from 0 to n minus 1, and the 1 over n 2 pi I nk is a delta function. This is really easy to prove. Similarly, to prove this, we can divide into two situations. First situation, n equals to 0. This is very easy. K from 0 to n minus 1. If n equals to 0, this term becomes to 1. And this is 1. And if n does not equal to 0, this summation becomes to use the formula of the power series. Is the nk minus 1 k n minus 1. Then this part equals to 0. So then we have finished the proof. Now by using this property, we can find the inverse transformations. First of all, we can write the discrete Fourier transformation is in this way: n minus 1 xn e minus 2 pi I n dot k n, and we multiply. And we can multiply kf 2 pi I m k n and this becomes 1 over n instead of the n root. And here n0 xn minus 2 pi I m minus m dot k over n. Then we sum over k from 0 to n minus 1. And in the right, we can sum over. Can change the sequence of the summation, so it becomes 2 sigma n2 n minus 1 xn sum k. n minus 1 by using this property, we knew this is the delta function, so this equals to n minus m. And here we sum n, so this term becomes 2. This term becomes 2xm. So we get the inverse transformation. Xm equals to 1 over n root sum k from 0 to n minus 1 xkf times e exponential 2 pi I mk over n. So this is the inverse discrete Fourier transformations. In one-dimensional lattice, we can have the 0, a. The first point we note as a 0 and the second as the 1, and their intervals are a, 2, n minus 1, a, with the periodical boundary condition, which means xn equals to x0, and it has a length L, total length L equals to n times a. Many times we just write they're in the forms of the function, so xn can be denoted as a xna, and it has the periodical boundary condition, which means xn equals to xna x0. Consider the Fourier transformations. We can write the xkf 1 over n root sum n from 0 to n minus 1 xn e minus 2 pi I n dot k over n. And we write them in the function of the real space coordinates. Sigma n from 0 n minus 1 x n a 2 pi I n a the n a here dot k, and rearrange this formula. I n a dot 2 pi k over n a, and this one we often mark as the q. Often mark them as a q. So it can be written as writing the voice sum n2 pi n a q equals to 2 pi k n a So, okay. So this should be written as the xq. F is the index of the Fourier transformation. xq. And the k, since n takes the value from 0, 1 to n minus 1, and the k takes the value 0, 1 to n minus 1. And in many times we can find the xfq also satisfy the periodical condition, which means the xf k plus n equals to xf k. This is really easy to prove because we write them in the definition. Because this part has a periodical condition, and a equals to, and this equals to e the full minus I 2 pi n k minus n dot minus I 2 pi n n n, and this equals to 1. So this is the xfk. So here we can find the q long. The reciprocal coordinates q is equals to 2 pi k over na, and the k equals to 0, 1, the n minus 1. If n goes to limit, so the q can take the value from the 0 to 2 pi over a. This is the open interval, 2 pi over a. But often, in many times, to make it more convenient, we take the periodical boundary condition. So k takes from the minus 2 n over 2, 0 to n minus 1. So the q can take the value of the pi over a minus 2 pi over a. So this is the Brownian zone, which means which refers to the coordinates that can of the reciprocal lattice, reciprocal space. So this is the Brownian zone of the one-dimensional lattice, the most simplest lattice. And also, of course, the 0 to 2 pi over a is also the first Brownian zone. But in many textbooks, they often take this one. Now we want to come to some more difficult part, is the three-dimensional case. The discrete Fourier transformations of the three-dimensional are defined in such way. X, K1, K2, K3, F equals to 1 over 3 from the n1 to 0, sum n1 to 0, n1 minus 1. 3 minus 1. 3. Similarly, we can define the inverse transformations. And we also want to write this in the way of we want to write them in such kind of way. X, the reciprocal lattice 1k 2k 3 equals to 2 and 3. Mm-hmm. 2 and 3. 1 A X A E I A Oh, is the okay? No, let's make some correction. And 2 and 3. The E minus I R 1 and 2 and 3 G K1 K2 K3. The R in 1 and 2 and 3 can be written in the primitive N1 A1 plus N2 N2 A2 plus N3 A3 GK1 K2 K3 K1 B1 K2 B2 plus K3 B3. And the A1, A2, A3 are primitive translational vectors. Translational vectors. It has this sum, so which means X R equals to X R plus N1 A1 X R N2 A2 X R N3 A3. This is the periodic boundary conditions. We want to make sure the R and 1 and 2 and 3 dot G K1 K2 K3 is satisfied equals to this, which means which means 2 pi dot n1 k1 over n1 plus n2 k2 over n2 plus n3 k3 over n3. And we just write them in the Cartesian coordinates. So the a1 can if R is in the cubic lattice, we can easily define a1 equals to a1i, a2 equals to a2j, a3 is to a3k, and the B, the reciprocal lattice, can easily be defined using these relations. So a1 b1 is 1 k1, a2 2 n2 k2, and n2 a3 dot b3 equals to n3 k3. So here this should be this. So the b1 goes to na1, b2 goes to na2i, b3 equals to 2, and 3a3j. Okay, but if the A is not a cubic lattice, which means a1 can be written in a11i plus a12j plus a13k, a2 equals to a21i, a22j plus a23k, a31i plus a32j plus a33k. So a1, a2, a3 is to write them in the matrix form to a13, a21, a22, a23, 31, a32, a33, I, J, K. And this one we want to make sure here we make some small mistakes in the tradition. We make some mistakes in a I B J, the delta I J to a1, a2, a3, because in the traditional textbook, solid state textbook, these are defined in the k1, n1, p1 plus k2, n2, b2 plus k3, n3, b3. So there's no need to add n here. And we want to satisfy these relations. So and we write B1, B2, B3, B12, B13, B2, 1, B2, 2, 2, 3, B3, 1, B3, 2, B3, 3, I, J, K. So in these relations, it comes to delta Ij, which means the A transpose needs to make a transposition. A1, A2, 3, B1, B2, B3 equals to identity matrix. So in the writing the A11, A12, A13, A21, A22, A23, A31, A32, A33 equals to B. So we need to find the B, B13, B21, B22, B23, B31, the B matrix. The coefficient of the vector reciprocal lattice comes to the A. Inverse, and the inverse of the by the basic knowledge of the linear algebra, it's very quite easy to calculate. 2, 3, A3 equals to, here is the coefficient 2 pi. There should be 2 pi. There is a coefficient. This is the A21, A31, A22, A32, and it should be A11, A12. Because there is a transposition. This is a transposition of the. Okay. Before we want to we want to write them because there's a transposition, and if we write the answer, this can be a little bit confusing. So for any matrix, x11, x12, stop using x. Okay. For any arbitrary matrix, A12, A13, A21, A22, A23, A31, A32, A33. The inverse is the determinate A and A11, A12. There's a transposition A13, 2, 1, A22. And here A is the algebra complement. Aij is the algebra of A. So here, take the transposition determine A11, A12, A13, A1, A2, A3. So here the B equals to B1, B2, B3 equals to, and we can check that equals to 2 pi A, determine A over 2 pi, determine A 1, 1, A1, 2, A1, 3. We can easily check is the A2 cross product A3 equals to A1, 1, 1, 2, A1, 3. So it can be right in this form A2 cross product A3. The determinant is the mixed product A1 dot A2 A3, which also means the volume of the primitive cells. So